Hey, welcome back, physics fans. Let's just continue on with lesson 2 here, work, power, energy. The first lesson that we did was on work, the necessary introduction one, and now we're going to just talk about two different types of energy, potential energy and kinetic energy. So as we move on, let's just start here. So the energy of position. If an object is in an unstable equilibrium, well, let's say in a stable equilibrium, work is required to move it away from its position. So to push a piano up the stairs, you will have to add energy to it. A piano is stable on ground level, so work is required to move it up a flight of stairs. Okay? Now the mass at the end of a spring has a distinct equilibrium position. So if we move it from its position, its stable position, maybe it's here is where its stable position is, and then we move it out to here, it required a force over that distance. And the mass, we'd need to do work. Okay, and therefore there is energy there. Since opposite poles of magnets attract and like poles repel, work is also required to pull the opposite poles of magnets apart. So if this is stable right here because they're attracted, it would require work to pull it away. Boom. So it would require work to do that. And here they're repelling and they're stable, but to push them together would require work. So to put them together, work would be done. Potential energy is work is put into an object to move it away from the equilibrium. Conversely, energy is released when the object returns to it. Oops, then piano slides down, ka-chang. And the piano releases energy as it falls down the stairs. The mass attached to the spring releases energy as it returns to it. Goes ding, 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 and starts bouncing back and forth, but at least it's swinging in. And the energy released in opposite magnet poles and opposite ones slam together because they're attracted, and these fly apart when they're released. So it's releasing the energy. The energy is released as each object returns to its equilibrium position. And the amount of energy that is released is equal to how much work was put into it to move it away from that equilibrium. We refer to that energy stored in an object due to its position or location as potential energy. Okay, the work you do to separate that, the work you do to separate attracting magnets becomes its potential energy. If the magnets are allowed to rejoin, they release that potential energy. There are many forms of potential energy: gravitational, lifting it up; elastic, stretching a spring; electric potential energy in a battery; magnetic and nuclear. And each of these requires a force. So we're going to focus only on gravitational potential energy. An object possesses gravitational potential energy if it is above a possible equilibrium position. How much gravitational potential energy does an object have? It depends on how much work would have been done to lift it above an equilibrium position. So it's sitting on the ground here, it's in equilibrium, we'd have to lift it up. So that was the distance up, and we'd have to lift it with a force. And how much force would that be? That would be the pull of gravity. Just remember that if we lifted it up, there's a force up and there's a force of gravity. And to hold it steady, or to lift it up at a steady rate, this has to equal this. At a constant speed, there's no acceleration, no net force, that has to equal that. So the lift force is its weight, is its force of gravity. So how much work is done? Force times distance. The force is mg. The distance is the height. So work is equal to mgh. So how much potential energy does that object have? Exactly as much work was done to elevate it. So the potential energy is mgh, and that is our formula that we use a whole heck of a lot in physics 11 and 12. mgh is potential energy. And potential energy is the change in energy and is measured in joules. Okay, now it's a change in energy because H is changing. M is not changing, G is not changing in this time because we're not lifting it out of the atmosphere way up high. So G is staying the same. So the only thing that's changing is the height. So mass is kilogram, G is in newtons per kilogram, and height is in meters. And you must choose where you measure your H from. And you usually choose the floor, right? We'll see in a couple examples here. A 5 kilogram block is lifted from the floor to sit on a ledge 1.5 meters above the ground. So here's the floor, there's our ledge, and the block is lifted so that it sits up on the ledge. This height here is 1.5 meters. The object's mass is 5 kilograms. So what is its potential energy as compared to sitting on the floor? When it's sitting on the floor, we say that its potential energy here is 0, because that's where our 0 point is, because we usually set it on the floor. Why is the potential energy 0? mgh, and h, how far is h away from the floor? 0 meters. So this is 0, so this is why potential energy is set to be 0 at the point where we measure from our height. So the potential energy final is up here, and that's just mgh, and the mass is 5, g is 9.8, and the height is 1.5. And when we pull that all together, we get 5 times 9.8 times 1.5 is 73.5. And the unit, joules. So what is the potential energy that this block has compared to when it is sitting on the floor? It has 0 here and has 73, so that it has 73.5 joules of potential energy with respect to the floor. A 200-gram computer mouse falls from a 35-meter high balcony and lands on the ground below. What is the mouse's change in potential energy? Change in potential energy, final minus initial. So we'll draw the building and the floor. We're going to set the potential energy to be 0 at the floor. And we measure the height up, and it's 35 meters high, but it actually comes down that much. Anyways, 35 meters. So the potential energy initial is way up high here, is mgh, and that is 0.2 kilograms. So there we go. There's the first trick. We have to put it in kilograms. The 9.8 newtons per kilogram. So the kilogram units cancel. That's why it has to be in kilograms. And then the distance up, 35 meters. It's positive distance up. Okay, so we'll multiply this to get to 68.6. 0.2 times 9.8 times 35. Oops. 68.6 joules. And that's the initial. The final, potential energy final, is going to be 0 because it's on the ground at the end. So the change in potential energy is potential energy final minus potential energy initial, and that is 0 minus the 68.6 joules. So the change in potential energy of the mouse is negative 68.6 joules. So there's a change in potential energy, and it's a negative. It's losing potential energy as it falls. The quick question now is, and here it is, what happens if I don't want to measure the potential energy from the ground? You don't have to. Let's go over here to pre-work solution here. If we set the potential energy to be 0 at the top of the building, so the initial is mgh and it's 0 because measured from the top, when we start at the top, the distance is h, 0. but the final is below. So MGH, it's a negative 35 because we're going down. And that's a negative 68.6 joules. So when we do the final minus the initial, we get still negative 68.6. That's what we had, negative 68.6. So did it matter if we put the 0 to be the ground or 0 to be the top? No, a little bit more negatives playing in here, but it's fine. But here's an eye-opener. Maybe, maybe not. What happens if I set the 0 point to be 20 meters above the building? What good heavens, who put it up there? Oh, well, let's work from up there. That's where potential energy is 0, I'm saying. So this is going down 20 meters to the top of the building where it began. So we use negative 20 as the height, and we get negative 39.2 joules is its initial potential energy. And then when it goes all the way to the bottom of the building, this poor mouse, it's at 55 meters below the 0 point. So we put negative 55 in here, we get negative 107.8 joules. And then when we take the final negative 107.8 joules and subtract a negative 39.2, so we're adding a 39.2, we get 68.6. So does it matter where you measure the potential energy from? No. You still get the same answer every time. So it's easiest at this point in physics to set it to be the ground. Do you have to? No. Okay, let's talk about the energy of motion. One of the possible results of performing work on an object is to accelerate that object to a different speed. Work can set a stationary object into motion, and work can bring that motion to a stop, that moving object to a stop. Work can increase the speed of a moving object, and work can slow a moving object down. Consider the simplest case. Work is done on a stationary object to set it in motion. Perhaps a stationary hockey puck is propelled by a hockey stick. Initially, the hockey puck is at rest. The stick pushes the puck forward with a force F and causes the puck to accelerate. A force over that distance, and the force acts over that distance d, accelerates the puck to a specific speed. Therefore, work increase the object's speed. Okay, let's just take a look here. Kinetic energy. When an object is pushed horizontally on a frictionless surface, it will accelerate. There is work being done, force times distance, and therefore the object is gaining energy. This energy is stored in its motion. An object that is moving has the ability to do work, like a hammer swinging towards a nail is ready to apply a force over a distance. So the work is force times distance. The force is the net force that's being applied to it, the push force, MA. There's no friction, so we're not subtracting it and stuff like that. So it's just MA, and the distance moved is D. So we get MAD. Now, just to do some kinematics work in here to get our formula, we take that the AD that's here is the AD here, so we move the VI over, subdivided by 2 or multiplied by a half, we get AD is this. Substituting this in, you don't have to ever recreate this, but you can see that I'm coming up with the formula that kinetic energy is 1/2 mv squared, and that the change in kinetic energy is 1/2 mvf squared minus 1/2 mvi squared, which is the final kinetic energy minus the initial kinetic energy. You can see the 1/2 mvf squared. Okay. So let's just do it. A 6 kilogram block is traveling at 3 meters per second. What is the kinetic energy that this object has? So the kinetic energy is 1/2 mv squared. So it's 1/2 6 kilograms, and v squared, 3 squared. So 3 squared is 9, times 6 is 54, times a half is 27 joules. So that's the kinetic energy the object has. Potential energy, we had negative potential energies, right? We saw them up there. We could have a potential energy that's negative. We had negative 68.6 joules, because that's the change in potential energy. And but then we had potential energies that were negative because we had a 0 point above. Can kinetic energy be negative? No, because the formula is 1/2 mv squared. V is squared. Yeah, V could be negative, but once you square it positive, so actually kinetic energy is always positive. Okay, a 2,000 kilogram car accelerates from 7 meters per second to 10 meters per second. What is this change in kinetic energy of the car? So the change in kinetic energy is kinetic energy final minus kinetic energy initial. And kinetic energy final is equal to 1/2 mvf squared, which is 1/2 m 2,000, and vf is 10 squared. So let's put this into the calculator, and it's going to be a nice number. 0.5 times 2,000 times 10 squared is, ooh, nice, as I said, 100,000 joules. Okay, and the kinetic energy initial is 1/2 mvi squared, which is 1/2 2,000 times 7 squared, and that's going to be 49,000 joules. So the change in kinetic energy is going to be the final, which is 100,000, subtract 49,000. So the change in kinetic energy is going to be 51,000 joules. Yay! What is the change in kinetic energy from 0 to 7? Well, at 7 it has 49,000, 0 is 0, so this is just going to be 49,000 joules. And what is the change in kinetic energy from 0 to 100? 0 to 10? I'm coming up with the answer already, 100,000 joules. So the amount of energy from going to 0 to 7 is 49,000. We'll need another 51,000 to go from 7 to 10. So that's interesting. From 0 to 7, even though this is more than half the speed, it needs 49,000. And here is another 51,000. So it only gets you 3 more. If you double the energy, a little bit more than double. Interesting. Anyways, that's our understanding of kinetic energy and potential energy now, these two formulas. And the next chapter is on energy altogether, bringing them all together and understanding how all of it works together. No pun intended with that word, work. Talk to you later. Enjoy the jingle here.